Alright, so in this video we'll be discussing a couple of introductory topics, and I will also work through a few mathematical examples which will give you an idea of the kind of math that we will see later on in the course. Okay, so the first thing that we'll talk about is measurement. Measurement is a very important uh, aspect of physics and science in general, because the way physics works is that you identify a mystery that you're trying to solve, and then you come up with some hypothesis or model which can explain that mystery, right? There might be several hypotheses which could possibly explain that mystery. How do you figure out which of these is correct? Which of these is the correct explanation for the phenomenon that you're trying to explain? Um, the only way you can figure that out is by identifying predictions of your hypothesis and then going ahead and making measurements to check whether those predictions are correct. So the hypothesis whose predictions are uh, verified by experiment repeatedly uh, is most likely the correct explanation, and that is what we call a theory in science. Okay, so measurement is a very important part of the process, right? I have one example of a famous measurement over here, which is the graph in this slide. You might or might not have seen this particular figure. This figure was very much in the news a couple of years ago. So I'm just going to very briefly go over what's being shown in this graph. This part is not going to be something that you're going to be tested on. So this is way beyond the scope of this course, but this is really cool. So I'll just quickly go over what this graph is telling us. So so first of all, what is this? So this graph is the first experimental detection of gravitational waves. And this happened in September of 2015. Okay, so what are gravitational waves? So let me just quickly give you a very brief background on that. Those of you that have taken physics in high school might remember that the force of gravity is given by an equation like this. So if you've got a mass over here, m1, and if you've got another mass over here, m2, the shapes and sizes don't matter, then the force of gravity between these two is given by this equation g m1 m2 divided by r square, where r is the distance between these two. Now you might have seen this equation. This is called Newton's law of gravity. But you might, if you've not taken physics before, you've probably never seen this, and that's absolutely fine. This equation will actually be the entire content of chapter 13. So we've already covered chapter 13. I'm just kidding. Okay, so anyway, so this is Newton's law of gravity. And it does a very good job of describing the force of gravity, an extremely good job of describing the force of gravity, as we'll see when we get to chapter 13. However, in between the years 1910 and 1920, Einstein realized that there is something fundamentally wrong with Newton's law of gravity. And so it took him almost 8 years, but ultimately he was able to come up with the true understanding of the force of gravity. So what is that true understanding? Well, you know that there are 3 dimensions of space, right? And we usually identify them as the x-axis, the y-axis, the z-axis. So those are the 3 dimensions of space. And there is also the dimension of time. The dimension of time is a little bit different than the 3 dimensions of space. But Einstein realized that these three dimensions of space and one dimension of time can be combined into a mathematical object, which is called space-time. You can understand why it's called space-time. It's got both space and time sort of combined together. So you can think of space-time as a sort of four-dimensional fabric. So that is what space-time is. It's like a four-dimensional fabric, right? What does this have to do with gravity? Well, if you have a large mass present somewhere in the space-time, or if you have, it doesn't have to be a large mass, if you have any mass present inside the space-time, mass tends to warp space-time, right? Okay, so that's another fact. And then if mass warps space-time, then objects respond to that warping of space-time by feeling a gravitational force. So objects respond to the warped space-time by feeling a force. So essentially, the summary of all this is that what we consider a gravitational force is not really a force at all. It's basically an object responding to the warping of space-time, right? So this is the general theory of relativity. Which was discovered by Einstein around the year 1918 or something like that. It is a very complicated theory. The mathematics of the general theory of relativity is extraordinarily complicated. Newton's law of gravity was this simple equation, gmm divided by r square. The general theory of relativity is described by this equation. Oops. The general theory of relativity is described by this equation. I don't know why my iPad is acting up. Okay, so you don't have to worry about what this equation means. If you're interested in this, of course, you can take Physics 8160 with me in the fall, which is general relativity for graduate students. Anyway, so this equation looks like it's a simple little equation, but it's actually a set of 10 nonlinear partial differential equations, which in most cases are too difficult to solve. You need a computer to solve them. So anyway, so this is the general theory of relativity, and this is the best understanding we have of the theory of gravity. All right, now there are two things that come out of, there are many things that come out of this general theory of relativity, but there are two things which come out of these equations, and they literally just fall out of these equations. One of them is the existence of black holes. What are black holes? Black holes are these incredibly bizarre objects which have infinite density, right? So you can think of a black hole as a point, a mathematical point, not a physical point. A physical point still has some spatial extent, but a mathematical point has zero spatial extent. So you can think of a black hole as a mathematical point which has infinite density, and a black hole is surrounded by something called an event horizon, right? Okay, but the point is that it's an extremely bizarre object with crazy properties, and you can think of it as a point of infinite density, right? So the existence of black holes is one of the things that comes out of the general theory of relativity. The second thing that comes out of the general theory of relativity is the existence of gravitational waves. All right, so what are gravitational waves? Well, I told you that space and time make up a fabric called space-time, and mass, the presence of mass, will warp space-time, right? So, one common analogy that's used to explain general relativity is that just imagine you've got you have the surface of a trampoline, right, with nothing on it. So then it's going to be a perfectly flat surface. That is what space-time is like in 4 dimensions when you have no mass in it. Everything it's just empty. But suppose a kid just jumps on or just gets on the trampoline and just sits there, then the surface of the trampoline will no longer be flat. It will be it will have a sort of warped shape because there's a mass on it. So that is kind of what happens when you put some mass in space-time. It warps the space-time around it, right? Now, what happens if the kid sitting on the trampoline just jumps up and down? So in that case, what would happen is that the warped space-time would wiggle around because the kid is jumping up and down. So there will be ripples spreading through the surface of the trampoline, right? And the same thing happens if you have some sort of event, if the masses in space-time are not sitting still, then if they're moving around, then there will be ripples spreading through this fabric of space-time. Just think about that. Ripples through the fabric of space and time, right? So those ripples are called gravitational waves. Now, both of these sound like absolute science fiction, right? Black holes, they're just so incredibly bizarre, and also gravitational waves, which are ripples in the fabric of space and time. But for a long time, people thought, even Einstein himself thought, that black holes are just mathematical curiosities, like they don't really exist in the real world. However, now we have plenty of evidence that black holes do actually exist. There is plenty of evidence there, and we know about many black holes. You might have heard that there was a picture taken of a black hole, though that's what constitutes a picture of a black hole is something that needs more discussion. But there was a picture taken of a black hole in 2018, I think. So anyway, so there's black holes do exist, and the discovery that I'm talking about right now in 2017 proves that gravitational waves exist as well. So how can you possibly detect these ripples in the fabric of space and time? Well, one way of doing it is, suppose you have a long tunnel, and suppose there's a gravitational wave that's passing by, right? So the gravitational wave causes things to so if you have a tunnel like this, what the gravitational wave is going to do is slightly alter the length of the tunnel. So the length of the tunnel will shrink and then expand, and then again shrink and then again expand. So the length of the tunnel is going to slightly vibrate when a gravitational wave is passing through it, right? Because space-time itself is vibrating, so the length of this tunnel is going to vibrate, right? Now, how do you measure that? Now, this effect is going to be incredibly tiny. And how do you measure that? Well, how you measure it is rather complicated. You use an interferometer, and that's why this experiment is called called LIGO, Laser Interferometer Gravitational Wave Observatory. Um, so if you are constantly monitoring the length of the tunnel very accurately, and all of a sudden you find that the length is vibrating, then you know that a gravitational wave passed by, right? So to do this experiment carefully, um, there was one LIGO experiment set up in Washington State and another one set up in Louisiana. And on that one day in September 2015, the Gravitational Wave Observatory in uh, Washington picked up a signal. And very shortly after that, like a matter of a couple of nanoseconds after that, the Gravitational Wave Observatory in Louisiana picked up the same signal, same identical signal, right? That tells us that a gravitational wave that was passing through the universe uh, was picked up by our two um, detectors, two gravitational wave observatories, right? Okay, and that is exactly what this graph is showing us. So if you look at this quantity strain, strain really means the change in length of our tunnel divided by, delta means change, divided by the actual length of the tunnel. Look at the scale of this graph, 10 to the power of negative 21. So that is an unimaginably tiny change in the length of the tunnel, and it's crazy that we are able to measure it. So the actual length of the tunnel L here was 4 kilometers, and when the gravitational wave passed through the tunnel, the length of the tunnel fluctuated by an amount which is 10 to the power of 10 negative 21 times 4 kilometers. That is a thousandth of the width of a proton. So it's insane that we can do a measurement with that kind of accuracy. It took many years. It took 30 years to be able to develop equipment that can measure things so minute. But it's amazing that we can do it. So what caused this particular gravitational wave to pass by um, through our two detectors? Well, it's actually an astrophysical event. So what is believed to have happened is that there were two black holes which at a distance of 1.4 billion light years away from us. So these two black holes were sort of orbiting each other. So they were going around in circles around some common point. So that's a fairly common thing. You have two objects orbiting a common point. And they were gradually losing energy, and as a result of that they started coming closer, orbiting each other closer and closer, and then eventually they just slammed into one another. One of these black holes had a mass of 35 solar masses, which means its mass was 35 times the mass of the sun. It's kind of written, it's sometimes just written like this. And the other one had a mass of 30 solar masses. And then when these combined, they formed a new black hole whose mass was 62 solar masses. So after they collided and combined, you had a new black hole whose mass was 62 solar masses. All right, so did the math work out? 35 solar masses plus 30 solar masses, does that give us 62 solar masses? The answer is no. So there is 3 solar masses missing. What do you think happened to the missing 3 solar masses? The answer is it got converted to energy. You might have heard of an equation E equals mc square, which tells you the relationship between mass and energy. So 3 solar masses worth of energy, 3 solar masses worth of mass got converted into energy as a result of this collision, and that energy spread out in the form of gravitational waves. So 3 solar masses worth of energy is truly, truly, truly humongous. So there was an enormous amount of energy released in that collision, and that spread out in the form of gravitational waves. And those gravitational waves were picked up 1.4 billion years later by our observatories on Earth. So that's absolutely, absolutely crazy. And so this measurement is this. So this is a spectacular example of a measurement which confirms the existence of gravitational waves. I must say that many other gravitational wave events have been detected since this first one in 2015, and this is an active area of research in physics right now, gravitational wave physics. All right, so I just thought I'd talk about that because it's a very fascinating discovery. All right. Okay. Now let's come back to Earth and talk about more basic things. So in order to do measurements, we use units, and there are 2 kinds of units: basic units and derived units. So what are basic units? A set of quantities, length, mass, time, electric current, temperature. The units of these quantities are designated as basic units. And any units which are combinations of these units are called derived units, right? So for example, speed would be a derived unit because speed is distance divided by time, right? So the unit of speed would be the unit of distance divided by the unit of time, meters divided by seconds if you're using the SI system. So speed is an example of a derived unit. Okay. So the SI system is what we will be using throughout this course. It consists of meters. The length is measured in meters, time is measured in seconds, and mass is measured in kgs. And this is the system of units that we'll be using throughout Physics 1 and Physics 2. There are 7 basic units in the SI system. Now you might wonder, why are these units chosen as basic units? Why don't we make speed a basic unit? This is entirely a matter of choice. So in the SI system, it was chosen to make these quantities the basic units, and other quantities which are combinations of these guys as the derived units, and that was entirely a matter of choice. You can have other systems of units in which other quantities are made the basic units. All right. Okay. So we talked about basic and derived units and the SI system. Let's look at an example. So in class, I will be using Top Hat to put these examples out to you. But when you're watching a pre-recorded video, what you should always do is pause the video when we get to an example like this or a problem, and see if you can solve it yourself, and only then resume the video and see and look at how I solve it. So what I am asking you to do is to watch actively. So don't just watch these videos like a movie. So feel free to pause the pause the video at any time, and particularly pause it when we get to these examples, and try them yourself before proceeding. All right, so the question here is, will area have a base unit or a derived unit? So please pause the video and see if you can figure it out. The correct answer is that area will have a derived unit. Why is that? What is area? So area is the product of 2 lengths, right? So if you're finding the area of a rectangle, for instance, you would do length times width, and so it would be meters multiplied by meters. So meters square would be the unit of area in the SI system. And so it's a combination of 2 basic units. I mean, they're the same here, it's meters and meters, and that's why it's a derived unit. Okay. All right, we're going to now briefly talk about dimensional analysis. So what is dimensional analysis? Dimensional analysis is the idea that when you have an equation, both sides of the equation should have the same units or the same dimensions, right? And so using dimensional analysis, it's often possible to deduce equations or check whether certain equations are correct, right? Okay, um, let's look at one example of that. So the quantity angular momentum is given by the formula L equals mv times r. And kinetic energy is given by the formula K equals half mv square. You'll be introduced to both of these quantities much later on in this course. So if you have not heard of angular momentum or kinetic energy, don't have to worry about it at all. We are only looking at the formulas which are provided. That's all that we'll need. What are the units of angular momentum and kinetic energy? Okay, so let's work this out. Angular momentum L is equal to, the formula for that is mass times velocity times distance, right? So let's see what the units of this would be. The units would be kg multiplied by, I shouldn't put an equal sign over here. The units should be kg multiplied by meters per second, which is velocity, multiplied by meters again. So this is kg meter square divided by seconds, and that's the unit of angular momentum. All right, what about the units of energy? So the kinetic energy, the formula for kinetic energy is half mv square. So the units of kinetic energy would be, in the SI system, would be, half obviously is a number, it doesn't have any units. M is kg and V is meter per second, and that's squared. So it's kg meters square divided by second square. And that's it. So this is the unit of kinetic energy. Okay. Do you know what this unit is called? This particular unit has a name. It's called a joule. So you're going to see this when we get to chapters 6 and 7 and talk about energy. All right. This particular unit for angular momentum does not have any name. Okay. Though you can see one interesting thing here. If you multiply a joule by a second, then you get, so if you multiply the joule by 1 second, by a second, then one of the s's cancels out and you get angular momentum. So if you want, you can write this as joules times seconds, but it doesn't matter. All right. Prove that the following equation is dimensionally correct. So kinetic energy is equal to L square divided by 2mr square. So this is one of the advantages of dimensional analysis. You can often check whether an equation is correct or not, even if you know absolutely nothing about that equation, right? Even if you don't know what the quantities stand for, if you know what their dimensions are or their units are, you can figure out whether the equation is correct. So what we have to verify here is that the right hand side of this equation has the right units, because it's equal to kinetic energy, so the units should be the same as joules. So let's see if that is the case. So K is equal to L square over 2mr square. So let's see what units that works out to. So let's plug in L. So that's kg meter square divided by second divided by, 2 doesn't have any units, mass is kg and r is meters, so that's squared. And let's simplify this. This is just algebra, so it's kg square meter square divided meters to the power of 4 divided by second square, and then that is divided by kgs and meter square. All right, so there's some stuff that cancels out. One of the kgs will cancel out and meters square will cancel out. So what do we end up with? Kg meter square over second square, and it looks like it does work out because that is joules. which is the unit of kinetic energy. So it looks like this equation is most likely correct from dimensional analysis, though dimensional analysis does not really, it tells you whether the equation is mostly correct, but it does not help you provide any help if you want to find out what the whether the numerical quantities are correct or not. So in this equation, k is equal to L square divided by 2mr square. You know that the L square and the mr square are in the right places. They work out. But what about this 2? How do you know whether it should be a 2 or a 2.5 or a 7? You have no way of checking whether this number is correct or not. But at least the physical quantities are in the right combination. Okay. All right. So the next example that we will discuss is this. It basically shows you a little. It requires a little bit of trig, and this kind of situation we are going to see a lot. So I would highly recommend that you think about this problem on your own and see if you can figure it out, and only then look at how I solve it. Okay. So please pause the video and see if you can figure out this problem. All right. So the problem is saying that a pendulum consists of a bob, which is a point mass, suspended by a massless string of length L. The pendulum is swung to one side so that the string makes an angle of theta with the vertical. What is the height? By what height is the bob raised? So let me just quickly draw this for you. So should I draw it over here, or should I just, maybe I'll just move on to a larger space. Okay, so let's do it over here. So we have a pendulum, right? So a pendulum is basically a string which is at the other end of which you've got a mass. Now we are talking about a simple pendulum. So in a simple pendulum, we assume that the string is completely massless, and the mass attached at the bottom, which is sometimes called the bob of the pendulum, is a point mass, which means that it's just a mass. It doesn't have any spatial extent. So we've just taken away everything that might be a complication. So we've made the string completely massless, and we've made the bob just a point mass with no spatial extent. And so that's called a simple pendulum, and we'll often talk about simple pendulums in this course. So what we have done here is that we have swung the pendulum to one side. Okay, so the length of the pendulum is L, mass is little m. So we've swung the pendulum to one side, and this is how it was earlier. I'll just draw that with a different color. And the question is asking, if we've swung it out by an angle theta, then what is the difference in height? What is the change in height of the bob? So the original height of the bob was this. The new height of the bob is this. And so this is the difference in height. And that is what we have to figure out. And we have to figure it out in terms of the length of the pendulum, which is L, and the angle theta. So this is also L. So in terms of L and theta, we have to solve for H. So that is what the question is asking. How do we solve this? Well, this has nothing to do with physics. It's just a little trig problem. So let me just name some points just so it's easy for us to refer to them. Let's call this point where the pendulum is suspended as O. Let's call this point as A. Let's call this point as B. And let's call this point as C. This point right here is C. Okay. So OA is obviously L. OB is L. Right? But when I say OA, I mean the measure of the line segment bit from O to A. So OA is equal to OB equal to L, right? So what about OC? So OC is, if you do SOHCAHTOA, OC is just going to be L O sine theta. So please make sure that you agree with that. OC is going to be L cosine theta, right? So we are interested in the height h, which is the measure of the line segment from C to A, right? So this is also h. So CA is what we are looking for. CA is clearly OA minus OC, right? So that's going to be L minus L cosine theta, and so that's L 1 minus cosine theta, and that is h, which is exactly what we were looking for. So I'll just write that here as well. So h, we just figured out, is L 1 minus cosine theta. Alright, so this particular situation is going to come up several times in this course, so please make sure that you are absolutely clear about it. Okay. Alright, let's do an example of a calculus problem. And so this kind of calculus problem will also come up many times in this course. So we are told, we are given a function, we are given some information about a function, and we have to figure out what that function is, right? So let me just pull that up on my computer as well. All right. So so in this next problem, we are told that there is a function y is a function of t, and that is what we have to find out, what that function is, right? We are given some information about that function. We are told that the second derivative of y, and derivative is written as dy dt, but sometimes it's also written like this with a prime, as you know from calculus. So it's a little bit convenient, more convenient to use the prime notation if rather than the dy ddt notation. So we are told that the second derivative of y, which is y double prime of t, is equal to minus 9 pi cosine 3 pi t, right? And we are given some other information as well. If you evaluate the function at t equals 0, then the answer that you get is 0. And if you evaluate the function, the first derivative of the function y prime at the point t equals 0, the answer that you get is also 0. So these are the three pieces of information that we are given about this function, and we have to find out what the function is, right? So let's see how we would do this problem. So you know that if you take the derivative of a function, you can reverse the process by taking an antiderivative or an integral. So if you have a function and you take a derivative, get a new function, and then if you integrate the new function, you get back the original function, right? So derivatives and integrals go in opposite directions. All right, so in order to get back the original function, what we can do is we can integrate the second derivative twice, and that should get us back to the original function. So that's what we're going to try to do. So we are going to use this rule for integrals. Let me just write down a couple of rules for derivatives and integrals in case you've forgotten. So d x of sine of kx, k is a constant, is equal to k cosine kx, and d dx of cosine kx is equal to, the derivative of cosine is negative sine, I think, minus k sine kx. All right, and from this you can also figure out the integral. So the integral of sine kx is going to be minus cosine kx divided by k. And you can verify this by just taking a derivative of the right hand side and see if you get sine kx. Oh, and the very important thing I forgot to write down is you should always indicate which variable you're integrating with respect to. So the integral of sine kx dx means integration sine kx dx means the integral of this function sine kx with respect to the variable x. So this writing this little dx at the end is extremely important because it tells you which variable you're integrating with respect to. All right, and what about integral cosine kx dx? That is going to be sine kx divided by k. All right. Okay, so that's all that we need in order to do this problem. So let's start with integrating y double prime once. So that would give us y prime of t, and that, so if you integrate it, so y prime of t would be the integral y double prime of t with respect to t, right? So there is one other subtlety here. When you integrate a function, you have to add a constant to it, right? So this is actually, so y prime of t is equal to y double prime of t dt plus an additional constant. And I'm sure you've seen this in calculus class. And in order to figure out what this constant is, you need to know the value of the function at one particular point, right? All right, so let's start working this out. So this would be the integral of minus, I should make a little more space. So let me just do this over here. So y prime of t is the integral of the given function minus 9 pi cosine 3 pi t dt. So that's going to be using our integrals that we have over here, minus 9 pi, you pull out the constant, and now you're integrating the cosine 3 pi t. So that's going to be sine 3 pi t divided by the constant 3 pi. I just use my use this rule. Okay, plus a constant, right? So this can be simplified to minus 3 sine 3 pi t plus a constant. All right, so now we need to figure out what this constant is. We are told that at t equals 0, the y prime is just 0, right? At t equals 0, y prime, oops. At t equals 0, y prime is equal to 0. Okay, I didn't need to write the t equals 0 over here. So let's use that information. So if we plug in t equals 0, the left side should be 0. So 0 is equal to c is what we are getting, and that just tells us that this particular constant happens to be 0. Sometimes students think that these additional constants are always 0 and we don't need to worry about them ever, but they are not necessarily always 0. You have to figure out what the value of the constant is by plugging in the given information. So we found y prime of t, the first derivative of the function y, is minus 3 sine 3 pi t. Okay, now let's integrate this one more time to get y. So y of t would just be one more integral of this plus a constant. So would be integral of minus 3 sine 3 pi t plus some constant. Okay, I'm using the same symbol c for the other constant, but there's no reason for these constants to be the same. Let's go ahead and do this integral. So you pull out the minus 3 and then you have to integrate sine. So when you integrate sine, you get minus cosine, right? So this would be cosine 3 pi t divided by 3 pi, and another minus, a minus comes out of the integration, which cancels out the minus that's already there, plus c. So that's y of t. All right. So now we need to figure out what is this constant c, and you can cancel out this 3 that appears over here. So for that, we use the fact that at t equals 0, y is also equal to 0. So let's plug that in. So the left side should be 0. The right side, when you plug in t equals 0, then you get cosine 0, which is 1, right? So you get 1 over pi plus c. And so from here you can solve for the constant of integration. So c is equal to minus 1 over pi. And if you plug that in, you get the final answer. Y of t is equal to cosine 3 pi t divided by pi minus 1 over pi, which is exactly the correct answer. It matches the answer given on the slide. All right, so please make sure that you understand this example very clearly, because this kind of calculus manipulation you will be doing a lot in this course. All right. The last example that we are going to discuss is this one. So you have a particle that's moving in the xy plane such that its x and y components are given by the parametric equations. X is equal to 2 cosine t and y is equal to sine t. And find the equation of the curve followed by this particle. So let us make sure that we understand what this problem is saying, and then let's see how we can solve it. And once again, if you think you can, even if you think that there is a chance that you might be able to solve this on your own, then you should definitely pause the video and try to solve it on your own before looking at the solution. Right? So just watching me solve a problem is not useful at all. If you can solve the problem yourself, that is far more useful than just watching me solve it. All right. So what is this problem saying? So there's a particle that's moving around in the xy plane. And so its x and y coordinates are always changing, right? To describe the motion of the particle, this problem is using parametric equations, which means that it's expressing both the x and the y coordinates of the particle in terms of a new variable, which is called the parameter. And the equations are 2 cosine t and sine t. So how are you supposed to find out the motion of the particle? Well, you can plug in different values of t. So for example, if you plug in t equals 0, then you find that x is equal to 2. So here are some examples. If you plug in t equals 0, then x is equal to 2, y is equal to 0. So that means when the parameter t is 0, then the particle is located at this point 2, 0, right? You can plug in t equals pi or something as another example. I'm just picking these values at random. Then x is equal to cosine of pi, 2 times cosine of pi, which is minus 2. And y is equal to 0 again. So at t equals pi, the particle is somewhere over here, and so on. So you can plug in any value of t, and you will find out the location. It will give you a certain location for that particle, right? So that is how you know what path the particle is following, by just plugging in successive values of t, as just more plugging in different values of t, you can figure out what path the particle is following. So that is one way of representing the path of the particle. And what this problem is asking us to do is to express the curve followed by the particle in a different way. Now, what is a curve? A curve is y as a function of x. So that's a mathematical curve, right? That's how you've been introduced to curves in your pre-calculus or algebra courses. So a curve is simply y as a function of x. So essentially what we need to do here is just mathematically what we need to do is we need to get rid of this variable t and try to express y as a function of x. All right. How would you do that? Your instinct might be to eliminate t from one of the equations and then plug it into the other equation. That's absolutely reasonable. So for example, from the second equation, t is equal to inverse sine of y, and then you can plug that into the first equation. X is equal to 2 cosine. Instead of t, you put in inverse sine of y, and so you have expressed x as a function of y, though we were looking at y as a function of x. So you can sort of continue this process, and you can try to find y as a function of x. And if you correctly work through the algebra, you will get the right answer. But there's actually a very elegant way of doing this problem. So this is approach 1, which will give you the correct answer. But the reason that I wanted to show you this example is because I want to introduce you to the other trick that you can, I want to show you this other trick that you can use, which is often more useful and much faster than this approach. Okay, so what we're going to do is approach 2. So here we are going to use the fact that sine square of anything plus cosine square of the same thing is equal to 1 always. It doesn't matter what theta is. Sine square of theta plus cosine square of theta is equal to 1. This is the most important equation in trig, right? So we're going to try to use this, right? So looking at our two equations, let's try to isolate sine and cosine and plug them into this equation. That's all that we have to do. So sine of t is y, right? So it should be true that sine square t plus cosine square t should be equal to 1, right? Now sine of t from the second equation is just y, so y square, and cosine of t, cosine is x divided by 2 from the first equation, so x divided by 2 square equals 1, and that's it. This is an equation which connects x and y, and it represents the equation of the curve. So this is the answer. And this is also the answer. In fact, if you love math, you can try and prove that this equation, let's call this equation 1, and let's call this equation 2. You can prove that equation 1 and equation 2 are identical if you love math. I'm not going to do that now, but if you're interested, you can ask me how you would do it, but it's not difficult to prove that. Approach 2 is what is my point, my goal of showing you this, because it's very important that to recognize that you can often use sine square plus cosine square equals 1 in these problems. There's another important takeaway for you from this problem, which is the parametric representation of a curve. So please make sure that you understand the parametric representation of a curve. So the parametric representation, just to repeat myself, is when you express both x and y coordinates as a function of another variable, which is often called the parameter. And so by plugging in different values of the parameter, you get different values of x and y. And so with those values of x and y, you get a curve in the plane. So that is called a parametric representation of a curve. And that is often much more powerful than representing a curve as y as a function of x. So the parametric representation is a much more powerful approach. Though in school you might have just been taught y is a function of x to represent a curve. All right, okay. So that concludes this first video, and all right, so we'll stop the video here.